Hi, everyone. Thanks for coming. Today, our speaker is Professor Lina Necib, who is a faculty member at MIT, who specializes in the study of dark matter and local galactic dynamics. She uses a combination of simulations, observations, and machine learning techniques to explore the dynamics of dark matter and accreting stars in the galaxy and neighboring galaxies. In the Milky Way and neighboring galaxies. And today she'll be talking about mapping dark matter in the Milky Way and dwarf galaxies. She also is giving a ITC lunch talk today and has time to meet afterwards if you would like to talk further after her talks. Thank you.
All right. Oh, I love it. Okay, so this should work. Hi. So thank you so much for having me. I have not been here that often, given that I am not that far away, so I should actually come visit more. So today I'm very excited to tell you about what my group has been thinking about in terms of mapping out dark matter in the Milky Way. So apparently, from the southern hemisphere, you would see a view like this. Unfortunately, I didn't get to go, and also I'm a theorist, so hey. But something this gorgeous is not to be missed. So I'll definitely try to go at some point. But this is the Galactic Center, where you will see a lot of stars, in particular some dust extinction here, which means because we're seeing the optical loops, it's a little bit harder to see. We can also see some satellites of the Milky Way, like the Large Magellanic Cloud right here and the Small Magellanic Cloud. But what I've been thinking about is a map that actually looks a lot more like this, which is dark matter. What would dark matter look like in our galaxy? So you would actually expect it to be centered around the center of the Milky Way, of galaxies, but also you might actually expect some very small subhalos that do not host a lot of stars. Thing is, we don't really know what dark matter is, and we don't know how it would be distributed in the galaxy at all. So which means that if this is lambda CDM, it's equally viable for dark matter to be, for example, warm, in which case you will end up not having those small scale structure, or it could be self-interacting, in which case things will be a lot more spherical. The density is going to be a little bit more even. If you have cores, you might have gravithermal collapse in some places, or it could be something else altogether, in which case we just don't really know. The thing is, the way that I've been thinking about it, especially because I got my PhD in particle theory, is that dark matter itself does not really need to interact with baryons at all, although particle theorists might say otherwise. But this kind of gives us a view of what dark matter is, because we know it interacts gravitationally. So trying to figure out what the map is of dark matter actually can tell us something about its properties, its self-interactions, its initial power spectrum, its dissipation if there is one. So what I've been thinking about is really building these glasses that take us from what you see from the stars right here to the underlying dark matter. Yes, I spent too much time actually making these glasses. It's quite embarrassing. Okay, so given that I have a pretty funky background, so my PhD is in theoretical particle physics, and I was writing Lagrangians and quantum field theories, which I try to very much not think about these days. I get asked a lot of, what are you? So actually, what I would like to do is, and the one thing that has been consistent throughout is that I've been trying to think about dark matter the whole time. So now what I use is a combination of astroparticle theory, that's what my PhD is about, but also data from telescopes, machine learning techniques, cosmological simulations, and galactic dynamics to really try to map out what dark matter is and try to kind of have like this big picture so that we can figure out, what the particle nature of dark matter is at the end of the day, but with as many tools as we have available. The way that I usually tackle this is throughout multiple sections of the Milky Way. We kind of break it apart. So the Galactic Center and Halo, trying to figure out what the phase space distribution of dark matter is there, in dwarf galaxies, the solar neighborhood, and in stellar streams. Unfortunately, I won't have much time to kind of go through the whole thing, so I'll be focusing on just these two today. Of course, all of this work is made by the kick-ass team that we have here at MIT. We had like a whole vote, and we call ourselves now the Cosmic Code Breakers, and we have merch. We made like a logo and everything just to have fun. But yes, so we've got a really incredible team that you guys should keep an eye out on and hire them at some point. You never know, because they're really, really cool people. Okay, so we've done a lot of work, but let's focus up on, oops, sorry. This clicker is just moving on very, very fast. I speak really fast already, but the clicker, I think, is just running. But we're going to focus on these two parts. So something that very much dates me, because apparently it's not cool anymore, is PhD comics. But this is what I think about dark matter. So dark matter is really clash of worldviews. So for the longest time, particle physicists, including myself, have been looking at smaller and smaller structures, and also smaller and smaller masses of dark matter candidates, and trying to build these theories that really try to explain this missing mass that we have. On the other side, astrophysicists have been looking at larger and larger structures from galaxies and galaxy clusters, and found out that there is, of course, this missing thing that's putting all of this and controlling all this dynamics together. And for the longest time, these two people did not really talk to each other, and I think that they should, because at the end of the day, what we were doing is trying to explain this one multi-scale problem that is dark matter. So that's kind of what inspires me to do what I do. All right, let's get started with the Galactic Center. How can we figure out how dark matter is distributed at the center of the halo? So if you go back to, well, freshman physics, or 8012, back at MIT, as I teach my first-year students, we have, if you're looking at the rotation curve, so rotational velocity as a function of radius, you would expect it to kind of go up as you have more and more enclosed mass, and then you would expect it to go down past the mass that you would see, and it's going to go down as 1 over root distance. With the work of Vera Rubin and collaborators, we found for quite some time now, so since the 70s, that rotation curves actually are a little bit more flat here, so they're not decreasing as fast as we think they are. So why does this matter? Well, rotation curves can tell us about the gravitational potential underneath it, which can tell us about the dark matter density. And the language that I'm going to be introducing here is really this kind of density profiles. So you will see me you'll see this plot like a billion times in today's talk. So this is the density as a function of distance. And there are, we don't really know what the inner profile of dark matter is, or at least for a fact. So from the work of Navarro and collaborators in 1997, we have what we call the NFW profile. We showed using numerical simulations that no matter what the scale is, if you have self-gravitating particles that are dark matter, the inner profile is going to follow this r to the minus 1. It's actually this kind of almost like a broken power law, where it goes r minus 1 in the inner part and to the minus 3 in the outer part. However, there are also other models that say, well, maybe, just maybe, the density profile of dark matter is actually chord, where it goes as r to the 0 in the inner part. The vocabulary that we'll be associating with this is called a cusp, and this is called a core. Of course, it's not really as binary as it is, like cusp or core. It's kind of a spectrum of things, or super cusps or super cores. But anyways, what we try to kind of think about is that this inner profile actually has a lot of meaning in trying to tell us what the interactions of dark matter are. So you might want to motivate this for the two people that we've encountered before. So for the particle physicists, they would care because the cusp is what is indeed expected if you have cold dark matter. But if you have self-interacting dark matter, it has some kind of interaction. It will actually distribute the heat in the inner part, and it will create something like a core. So if we actually find a core, that would be quite relevant because it will tell us that dark matter does have some self-interaction. Additionally, it will also affect dark matter detection because, for example, for indirect detection searches, dark matter annihilates. So here you have two dark matter particles. They will kind of annihilate or even decay into a lot of different things, same amount of particles that we later actually detect right here. These thinner matter particles could be photons, positrons, protons, anti-deuterium, anti-helium, all of the neutrinos. All of these are actual searches. I'm not making them up. But basically, what you would want to know is how much to expect from dark matter to give you whatever particles that you see, because what you're going to be looking for is an excess on top of what you are expecting from baryonic physics. The interesting thing is about this process itself is that the signal is going to be proportional to the density squared. And the reason for it is because you need two particles to find each other. This is for annihilation. For decay is going to be just density. So you can see here is that if your density profile looks like this, if you're off by an order of magnitude or two, the signal is going to be very, very, very different, right? The actual expected signal rate changes by quite a bit. This is kind of a very important point, especially because when I was back in grad school, my office mates were calculating these intricate loop diagrams with Sommerfeld enhancement about dark matter annihilating in the Galactic Center for this. And they spent like a year calculating these, and they were very proud to have it down to 10% error on these very complicated cross sections. And I'm like, great, but this is off by orders of magnitude. So, you know, you need to figure out, this is a more critical problem. All right, so from the astrophysics side, this is also very interesting, and especially because it tells us something about galaxy evolution and what galaxies actually are supposed to look like. So this is a theory paper, so a theory diagram, where on the y-axis we have the stellar mass divided by the halo mass, but you can think of it as basically like the galaxies and their galaxy masses from the ultrafaints all the way to the Milky Ways. And on the y-axis we have something kind of like this inner profile, but it's a bit of proxy because it's a little bit defined, a little bit weird, but we don't have to worry about it. The most important thing is that core is very close to 0 and cusp is more like 1.5. And this is because you're defining it as a slightly outer radius. So the open circles here are simulations that only include dark matter. And as NFW showed us back 20, 30 years ago now, a long time ago, that it is expected very much to be cuspy across all multiple scales. However, once you start including baryonic feedback and stellar feedback, you are expected to see things do change. So for the smallest galaxies, they don't have enough stars to make much of a big mess. But as you go up close to the LMC mass, stellar feedback, stars exploding and kicking a lot of matter from the inner part, actually do affect this distribution, and you end up a lot more cores. And then for the Milky Way, things are not as efficient, but of course the mass of the Milky Way is a big unknown, so I don't know if we're expected to be here or here. So it is very interesting for us to really have data points for a plot like this to understand the effect of baryonic feedback, and that will help us have more accurate simulations to really understand what, how galaxies form. Okay, so going back to our rotation curve, Vera Rubin did it in the 70s. We can do it in 2024. Famous last words. Because the Milky Way circular velocity, or rotation curve, is actually a lot more complicated because we're right in it. So things are a little bit harder than you would expect. But if we wanted to do it, you would need 3 ingredients. You would need the velocities, the distances, and some theory magic modeling to make sure that everything is done correctly. So if we start with the velocities, well, the cool thing is that we have, /had, a wonderful space mission called Gaia that has scanned the sky and provided us with motions of 1.5 billion galaxies that has basically 5D kinematics for, and a subset of 33 million, at least as of DR3, that has RVs, or radial velocity measurements, in which case you can kind of put it together as 6D phase space distribution, which is quite incredible. Great, we have some velocities. Gaia DR3 has been quite powerful. If we move to distances, yes, Gaia is very powerful, but distances based on parallax are iffy at large distances, and that's because the changes are very, very small. So, for example, if we live right here, we would expect about 10 kiloparsec as the distance for the stars that Gaia can provide distance measurements accurate to up to 10%. Beyond that, it really kind of degrades quite quickly. And what I like about this plot is that, or this figure, is that there's like this little circle here, and it's not just to tell us where the sun is, but it's the extent of the previous mission prior to Gaia called Hipparchus that ran from 89 to 93 and gave us about 800,000. So this revolution of 800,000 stars to 1.5 billion it still boggles my mind, even though now we take it for granted. Okay, so Gaia is very extremely powerful, but distances are a bit problematic, in which case what we wanted to do is use a data-driven model to compute such distances. And for that, we used apogee, or high-resolution spectra, which look like this. I can't read this because still I'm a theorist, but one of my students who just graduated has been co-advised by myself and a Freebull, so he can do theory and can read this, which is pretty incredible. So for the technical corner, basically what we do is we take the flux in a lot of these bins, about 7,000 bins for high-resolution spectra, combine it with photometry from different bands, from Gaia, WISE, and 2MASS. So basically you have so many features. And then what you're trying to do is build this almost linear, but it's not really a linear model in which you put in, you're trying to fit in all of these parameters to give you distances. So basically what you get is what we call spectrophotometric distances. And indeed, if we test those on the velocity, on the distances that Gaia already does very, very accurately, we can see that it follows the way that it's supposed to. So basically, we get these high-resolution spectra from apogee, as well as some photometry to kind of put things together to try to, really it's all about trying to estimate how much dust extinction there is through all of these bands and try to get accurate distances. This, of course, comes at a cost, and the cost is statistics, because from Gaia, we take those 33 million RVs, and we have to go down to what apogee crossmatch actually has for us, which is, actually it starts at 100,000, but with cuts, with a lot of different cuts, you end up with 33,000. So we lose about a factor of 1,000. That's unfortunate, but 33,000 stars is still a lot of stars. So we can actually do some real science with it. Great. So we've got the data. Now let's try to model things and try to make some rotation curves. So this work was led by my recently graduating student, Xiaowei Oh, who is absolutely incredible, a real powerhouse. And in this work, we had two papers, one with the initial rotation curve and one that we posted a month ago. And I'll be talking about both. But basically, we're going to start filling in what this plot is. So on the y-axis, we have the circular velocity. On the x-axis, we have the distances. And these tiny red dots with arrow bars on them are the data that we have so far. Excuse me. The gray lines right here are the ones from the previous measurement done by my colleague Christina Eilers in 2019 with DR2. The pink region here is our initial systematics kind of estimate. So we would expect that, our data plus systematic will look like this. What I usually like to put in perspective is that we should not be taking this for granted, because pre-Gaia, and not that long ago, we had rotation curves that looked like this for the Milky Way. So this is in 2017, not that long ago. And you can see what the axes are. So here, this is a 600, this is 300. So this has been a real revolution in terms of data. And for the longest time, the field has been statistics limited. So we were living in this regime, which means that details of the modeling didn't really matter if you live like this. Now I will be arguing that we live in a different regime in which we need to nail down the modeling quite well. So the interesting thing that we found, and it was corroborated by another two groups, results from two separate groups, is that the rotation curve was declining at large distances. That's a little bit problematic because the whole point of rotation curves is that they're flat, especially at these distances, 25 to 30 kiloparsec. So something was happening here. you can actually make some dark matter fits. If, like me, it's very hard for you to actually see that it's declining, and indeed it is. If we're trying to put this in terms of density profiles, and we fit it with a generalized NFW, which is basically an NFW, but the inner profile is this free parameter gamma. The annoying thing about it is that it's related to this one. It's trying to kind of bring this one down, ends up bringing this one down with it just because of the functional form. So these are purely limitations of the functional form of the modeling. You end up with a density profile that looks like this. You might think, well, okay, density profile is like that. Great, like there's no problem. The thing is, it is actually a problem because then it's going to be in tension with a lot of other results. So if we were looking at the enclosed mass as a function of distance, and we're only looking at the part where we have data for our measurements, which is here in black, then, okay, it's probably 1 sigma away from the other measurements. But then, and you can see where I'm going with this, if you try to compare it to results from globular clusters and stellar streams and things that are far away, we end up way off with a very, very light Milky Way. So something obviously is up around here that we really need to understand. And there have been some papers that said like, oh, Keplerian motion or something. But what we wanted to do is kind of go back to the drawing board and try to revisit the assumptions that we made to try to figure out where could have things gone wrong. So to do that, we kind of divided the assumptions that we can think of into 3. So observational selection function, axisymmetry, and dynamical equilibrium. The observational selection function is basically asking the question, is Gaia, and actually also apogee, picking some stars over others? Is it picking out only the slower stars and further distances? Is there some biasing there that's happening? And to address this, we actually build these synthetic surveys based on the FIRE simulations, which are publicly available if anybody wants to play with them. And we ran our whole pipeline on these synthetic surveys. Synthetic surveys is basically answering the question, what would Gaia see if it lived in the simulated galaxy where we actually have all the other rest of the answers? And what we found is that actually there is no observational selection function bias. So whatever Gaia was picking, and we also did some mock of what apogee was also picking, it didn't seem to affect the actual results. So there was not like a specific type of stars that we were biased more towards it. Moving on to the axisymmetry part. Well, axisymmetry is basically, we assume that our Milky Way is very much has like the cylindrical symmetry or axisymmetry. So what we can do with synthetic surveys that we don't really have access to in data is kind of run our analysis on this chunk of the sky where we kind of live right here, and then run it somewhere here and try to see how far away the results are. Do we get 2 very completely different rotation curves? Actually, we did it in 10 different spots around the Milky Way in 9 synthetic surveys. But either way, basically that's the idea. And what we found is that axisymmetry is a really bad assumption, something that is somewhat expected at this point, but it ended up causing errors from 5 to 20% errors, which is a lot more than we had expected for it. You move on to dynamical equilibrium, and although the effect of big mergers that we could track in our simulations, kind of you have something that hit and everything kind of, all the rotation curves kind of go wild, after a dynamical time or 2, kind of things kind of do go back to what it was, but you still end up with a lot of other issues because of disk flaring and asymmetric drift that you're not taking into account properly, although you try to model it, but it involves higher and higher orders into your genes modeling. So this is what kind of we categorize all of it under dynamical equilibrium, but it just shows us that it's not really a good assumption. Again, this is within the very small error bars that we have. So putting everything together, if we have our data points here, and that's our initial estimates of our systematics, and we try to fit it with 2 separate functional forms for the dark matter, like we talked about earlier. One here is the generalized NFW, and this one is an INASTO profile. Again, this is just to get at, yes? Please.
That was very interesting, but some of the simulations show that dark matter can be tilted with respect to the stars. Like
Yeah.
the distribution of dark matter may not be like following the stars or vice versa completely. So maybe that can be a good explanation for it.
So basically what we use for the stars is that we're not trying to kind of go from directly from the map of the stars to the underlying dark matter. But basically we're using the stars as tracers in a gravitational potential, right? And what they're trying to tell us is what we're trying to fit for is what is the gravitational potential of the dark matter along with that of the stars and the gas, which is here that we have, right? So yes, they are not one-on-one. The problem is going from there, you have to assume that your galaxy is in equilibrium and nothing really funky is happening, which what we're arguing is not really the case. And indeed, that kind of validates what you see as well. Yeah. Great. So to kind of, yes, these two distributions are just so we can kind of change the functional form. And what we found from these simulations is that although we first thought that our systematics looked like this, a more accurate representation is for them to look a little bit more like this. And once you take this into account, your rotation curve kind of turns from this to something a little bit more NFWE. And yes, for the enclosed mass, we made a new plot, and yeah, my student changed the colors. So now it's the generalized NFW is the black line. And these are the points from the literature, which we don't fit for. We only fit for our data points. But this is the extrapolation. And we see that now we're not in disagreement. But really, the point that we were trying to make is not really about trying to fit the enclosed mass, but having a more robust way of getting rotation curves. So, OK. We have these rotation curves, and everything kind of, well, hopefully, is much better suited now. The thing is that we're kind of thinking about is that this might be, well, this might be a very extreme view, but this might be the end of the end of the road for rotation curves, just because the thing is with rotation curves is that you're kind of taking your entire galaxy and putting it into one dimension, which is like you're projecting it into R, right? Which means that you really need that axisymmetry. And you need so much of that dynamical equilibrium because you're going from velocity measurements all the way down to this, which we don't think is going to happen. Well, or at least because our data is so good at this point, is that these systematics really need to be taken care of. So it might be a good opportunity to kind of look for different methods. So what we're looking for right now is using some diffusion models to and methods that we borrow from large-scale structure for people who are doing kind of galaxy halo connection, where they use the galaxy map to try to infer the dark matter halo map. We're trying to do this on smaller scales. Very initial stages, the baseline does slightly better than random, is what my student told me. So yay, we're getting there. But it is kind of a good opportunity to start thinking about it in a lot of different ways. The other thing that I would like to kind of yes?
Can I ask one question?
Sure.
This sort of expanded?
Yes.
So that's not that's in a sense the systematic of the possible messiness of the galaxy.
Yes.
More so than like the way we make the measurement. It's like that we're making a measurement
Right.
in our local neighborhood or corner of the galaxy or whatever you.
That's right. So basically, the way that we do this, for example, is that when we did this, did this on our synthetic surveys in multiple spots, we tried to figure out, okay, how much does it vary depending on where we are in the galaxy, to take into account kind of like some estimate of how bad the axisymmetry is going to affect our simulation.
How much ability do we have to, I don't know, look across the galaxy at a slightly different slice
Yeah,
for, say, the red giants or something?
No, that's fair. So currently, and my student actually tried to do this with the 33,000 that we have and kind of split it. The problem is that you get such a big hit in statistics, it's very hard to kind of disentangle.
Okay.
So what you want is a little bit further. SDSS 5, I think, is actually going to give us a little bit more expanded view, so we can kind of sort of do this. And it's kind of, it's also a bit on our radar to do. And the next thing that we're looking ahead of, is, as I will mention shortly, is also the Galactic Plane Survey Roman, that hopefully kind of will get us a little bit more of a bigger view that way, so we can go a little bit further and try to put this together. But I also think that that doesn't kind of stop us from thinking that maybe there will be a more, like a better method that takes into account like that doesn't kind of project everything, and you're trying to actually put it in terms of a map where you're trying to kind of build some connections. But yes, the data is going to get better for sure. Yeah. Great question. So the thing is, you can see that our data stops here. Technically, it doesn't really. I think we have a few more points here, but we didn't model them there because that's where we know for a fact that axis symmetry is going to really go wild, because you're getting into the regime of the bulge and the bar, and things are going to be a lot messier.
Okay.
So we didn't do it, but this is what I'm going to talk about right now. Because at the end of the day, great, we didn't fail at rotation curves, but what we want is to fit in dark matter. And really, most of the difference is going to happen in the inner part, which is what we're actually looking for those cores and cusps. So what I want is a lot of data there. And we have a little bit of it, again, from maybe like one bin over, but it's very, very hard to get inside. And although I only took one astro class in my life, and somehow I ended up in the astro division in MIT, they didn't seem to much. I learned one thing in that astro class is that if there's anything that goes wrong in astronomy, just blame the dust. See, I learned something. Cool. So the problem here, it's very dusty towards the center of the galaxy, and it's really hard to get some data there. But good thing is that we do have, and we're going to keep going with the glasses metaphor, is that we will see through dust glasses. Good thing is that we have those. A few multi-billion-dollar one, like JWST, for example. And so we can actually look into that, although that's very, very expensive. But there are also other methods that we can do that we would explore, to get more data. The latest thing is that on Monday this week, like 3 days ago, we submitted a proposal to look for medium resolution spectra with Fire and Magellan to try to get some radial velocity measurements to some of the stars there and try to build a good data set. However, lots of challenges, right? We want the same ingredients that we had before. It's just that we have even more problems now. So for the velocities, we need to see through the dust. Good thing that there are some, near IR stuff that we can kind of use. And we don't have the data yet. Well, how can we address this? Well, we have some telescopes for it. JWST is one. The roaming galactic plane survey is something that we're very excited about and looking for. We have some apogee data a little bit, but so there is some data that we can propose for. So we can make some progress there. Definitely some progress over the next couple of years. Well, if Roman is ever launched, we don't need to go there. The thing is, distances are even harder of a problem here because they're hard to find to begin with. And the center of the galaxy is even worse. So what we've been thinking about is looking at catalogs for RLRA, or stars that we actually know, or know somewhat distances. And we found some catalogs for RLRA with proper motions and decent distances, which are the ones that we propose for to get some RVs, and hopefully we get some good measurements for the 3D. Velocities. Modeling, well, all the previous challenges in modeling hold, and we know even less about the center of the galaxy. So that's going to be a pain. The thing here is what I was talking about trying to use new methods or diffusion models from these large-scale structure, and trying to go through the literature to understand what's going on with the bar, and mainly to figure out a way to get away with it, to get around it, and try to get as close as possible to the center of the galaxy. I don't think we're going to go into like the inner 1 kiloparsec. That's too messy, but I think if we can make some progress going from right now 6 kiloparsec down to maybe like 4 or 3, hopefully that will help us disentangle some of the dark matter modeling. So that's all the things that that's gonna keep us busy for the next couple of years. But in the meantime, what we can do is actually put on theory glasses and try to see what do we actually expect for the inner part of the profile. Like we did talk about NFWs, we did talk about, but baryonic feedback. But like, can we put all of it together to figure out exactly a range of possibilities? For that, we're going to use simulations. So the collaboration I'm part of is FIRE, which stands for Feedback in Realistic Environments. And in FIRE, we have zoom-in simulations of Milky Way-like galaxies, just like this one. What I love about this is how many mergers actually kind of hit, and then we still end up with a beautiful spiral galaxy with a wonderful disk to it that is somewhat stable. Great. So what we want, after it gets to redshift 0, is use these simulations to try to understand what is expected from that inner profile. In particular, this is a project that was led by my student Abdelaziz Hussein, and then we posted it in January or February, so very early this year, and trying to see what we expect in the inner part. And for this, we're going to go into very, very bad PowerPoint animations, so get ready. Dark matter is here, and we've got gas. That's how galaxies form. This is what the potential of the Milky Way looks like. The good thing about gas is that it radiates. Once it does, it kind of collapses and forms stars, which deepens the potential well. If the potential well is actually deeper, that brings in some of the dark matter into it. So this is the process that we're going to call, that we call in the literature, adiabatic contraction. So through this whole thing where the gas radiates and kind of like cools and gets towards the end, brings in all the dark matter with it, everything kind of moves in the inner part, and that's kind of increases the density and kind of moves to something cuspier. However, we have an opposite effect, which does this, where this is that signifies the end of a star's life and explodes into supernova, which kind of shoots a lot of the material out, and that makes the potential well a little bit less deep, and that takes some of the dark matter out with it. Okay? So this process can be seen in simulations, and for that we looked at 4 sets of simulations: Auriga, Fire 2, Vintica 10, and TNG 50. This is a density profile, density profile as a function of the radius, and the reason that we have bands is because we picked 6 galaxies just to kind of have a galaxy-to-galaxy variation here. What we can see is that the 3 simulations that I'm not a part of agree, and Fire 2 is a little bit out of it. So let's try to understand what's going on there. If we take into like the pen and paper theoretical prediction for adiabatic contraction, right here, and divide it by what you actually observe from the hydrosim, so kind of like theory expectation to simulation. If it is 1, then you would expect that it means that adiabatic contraction, or like the actual theoretical expectation of adiabatic contraction, is a good way to describe what you're actually seeing in the simulation. This is true for Auriga, Vintica 10, and TNG 50. However, if you end up with a simulation that has very, very strong feedback, like Fire 2, you're going to kick out a lot more material. That kind of cores you a lot more, and you end up with this kind of range where things do shoot up. So what we wanted to do is take all of this information together and figure out what is the range of possibilities for cold dark matter for the Milky Way itself. So again, density profile is a function of radius, and basically what we use is the stellar profile for the Milky Way itself. We apply adiabatic contraction that takes us to here, like this blue line over here. Of course, again, the range is just because we have multiple galaxies. And the strong baryonic feedback is here in the red. So the range is going to be, if we didn't say which simulation is right, which one's wrong, but where it's going to be somewhere, or at least what we're expecting is that it's going to be somewhere between adiabatic contraction and very, very strong baryonic feedback. And this is kind of us putting our uncertainties all together. So that is quite interesting, especially for dark matter indirect detection. where a lot of the experimental papers end up using multiple different profiles because we don't know exactly which way it goes. And what we wanted to do is provide kind of the community with like a possibility of ranges that we can put as systematics, which hopefully will work towards decreasing in the future with more and more results. The other interesting thing that I would like to highlight pretty quickly is that if you're looking at dark matter annihilating in the center of the galaxy, for example, the GeV excess from a decade ago now, the annihilation, a lot of the argument for the annihilation being from dark matter is that if the map of the annihilation is actually very spherical, that's probably more dark matter than some stellar process that we just don't know. What we found is that indeed that is true if you have adiabatic interaction, but that it's not so true if you're pushed by strong baryonic feedback. You end up with dark matter being actually in the inner part distributed very close to the stars, which means that it's not an argument that you can just make as lightly, and it's something that we need to be taking into account. Great, so kind of putting everything together, the theory expectation kind of gives us a range. Core NFW, for example, is extremely unlikely, just because you need to be kind of pushing so much baryonic feedback even stronger than fire, which is very, very hard to bring the density profile, at least for cold dark matter that way. Which means that if you end up seeing it, it's probably not baryonic feedback and probably self-interacting dark matter or something else, dark matter property. The updated fit looks a lot more like that, which is consistent with what we would expect. And what we want is, at least over the next couple of years, is try to do better here and try to narrow down this band, try to figure out exactly what is going on in the inner galaxy. And because right now, this part here of the line is still an extrapolation. Great. So before I move on to dwarf galaxies, are there any questions? So I can drink some water. Yes. Yeah.
So you started off, and then you found that there was a tension between your results and other results in the literature. And then you expanded the estimated error bars based on the systematic, and it looked like something less than a factor of 10. But the tension looked pretty severe on a log scale.
Yeah.
And then it seemed like it went away.
Right.
So how did it?
How did that happen?
Yeah.
Okay. Let me go back. Yes. So because let me just do it this way. So most of the tension was kind of driven by the last few bins, really. Here we go. So if you go, yeah, so for example, for the inner part, it's not so bad. It's more about the slope rather than anything else, if that makes any sense. So if you kind of expand, expand the systematics based on what we see in simulations, the more, flatter slope is a lot more possible, right? And if anything, it's more preferred than kind of this slope going down. Which is quite limiting here, and that's really what changes that density profile. It's really the inner part, the outer part. And here, the functional form plays a role here, which is why we're not kind of going with, oh, this is exactly what the density profile of dark matter is going. It's more about, oh, if you underestimated this, you might end up in tension, which you can get rid of. But this is not the final story, because again, the functional form plays a role here. What you would want is something a lot more flexible so that it follows the data without too much extrapolations. Did I answer your question? Yeah.
What have we learned from external galaxies? As an outsider, it kind of seems like there's a lot of variation in rotation curves.
Yes. And there are, let's see. So yeah, okay, I don't think I have this plot, but basically there is for H1 rotation curves, there is this figure that is very similar to the theory figure that I was showing of the inner profile as a function of mass that has been done with H1. for some of the smaller galaxies, which is really, really interesting. I think ideally what I would like to do is actually using this with the stars. And the reason for it is because basically, each one you end up kind of looking a little bit on the outer edges and you're extrapolating in, versus the stars are tracers on the inner part. And if they work, you would end up with a more robust kind of statement. Ideally, what you would want is to have it with multiple probes. You have the kind of the H1 one, and then the star ones that probe the inner part, again, to kind of get rid of this extrapolation or dependence on functional forms and any of this stuff, if that makes sense. Yeah. And the Milky Way is, well, the best place that we have the most data for, but it's also messiest. So, yeah, it makes it more challenging.
But aren't there, for example, like velocity maps of integrated light in M31, for example?
Right. Yes, there are. You're not going to end up with this level of error bars, though.
I see.
Yeah.
I see. So it's a precision.
Exactly. So now I think we're
Okay.
moving towards kind of, yes, precision astronomy, which
Yeah,
is,
I see.
yeah, very
Okay.
different.
Understood.
Yeah. Excellent. Okay, so in the last 10-ish minutes, we're going to veer off to dwarf galaxies. And basically, we're playing the same game, but really trying to get the density profiles of dwarfs. And the reason for it is because the astrophysicists would be very interested in this inner part. Does this tell us exactly how galaxies evolve the way that we think they do? And the particle physicists also do look at dwarf galaxies for signals, mainly because they don't have as messy of a background as the Galactic Center does. The problem is also they have a lot less dark matter, so it's going to be a smaller signal. So in a lot of previous work, including some back in 2015, we found out that in some galaxies, if you were to fit the rotation curve with a core or a cusp, you might end up with a core that is actually preferred. And again, for these small galaxies, baryons don't really do much, which means that if you actually end up with a core that you can trust, it means that there is some interesting dark matter physics that's going on. However, it's very hard because you have to assume that the galaxies are in equilibrium and there are no binaries. Actually, there are lots of binaries, but the binaries, at least the stars that you're looking at, are not in binaries where you're only looking at the motion of one and not the other. And the problem for these galaxies also that most of them, we don't have really proper motions. You only have radial velocity, so you have to make some assumptions about how the anisotropy is distributed. You have to assume that they're spherical. Anyways, it's a lot of different assumptions. So back in 2020, what we wanted to do, actually we were tackling a completely different question, which is the effect of binaries, until we found out that the standard method of using stars, not H1, but stars, to get density profiles of dwarfs is actually quite problematic. And the reason for it is because we generated these realizations of galaxies that just have these ideal, pristine kind of situation where everything is spherical and dynamical equilibrium, nothing goes wrong. And we applied genes analysis to just try to see, do we get back what we put in? Again, very, very standard. And what we found is that, this is again the density profile as a function of distance, that you look, if you have only 20 or 100 stars per galaxy, you might be very way off. So if you're looking at 10 to the 9 solar mass galaxy and you're fitting it again with that generalized NFW where a cusp is 1 and a core is 0, we look here for the 20, 100, 1,000, and 10,000 stars per galaxy, again in these idealized situations. And the rows here are for the errors, so so measurement errors of 0, 2, or 5 kilometers a second. What you would find for, again, massive dwarfs here is that in ideal cases, definitely 20 stars, it's going to spit back your prior. Like basically, that's exactly what it's doing. With 10,000 stars, you can disentangle a gamma equals 0 from a gamma equals 1. And if you increase the errors, even with 5 kilometers a second for 10,000 for a 10,000 star system, sure, you can still do it. But again, this is because you have a very massive system with a very large dispersion. Take this to the ultrafaints with 10 to the 7, and all hell breaks loose, even with 10,000 stars, if you don't have very good measurements. And it's very, very hard to get these measurements down. So what we ended up thinking about is that, okay, we needed to build a method where we get a robust inner profile of dark matter. And Jane's analysis, which is kind of the standard here, has a lot of issues that even in the best of cases, you need a lot of statistics that is very well measured. So what we did is used simulation-based inference and graph neural networks to train a model to get those density profiles. So this has kind of multiple steps. The way that I think about it is that we generalize these idealized simulations is not even the word here, realizations. We build a graph, and the reason that we're using graphs is because stars that are close enough together will be probing similar potentials. So they will have some connections that it's good for them to kind of talk to each other. You train the network on these idealized cases and apply it to data and use normalizing flow to kind of get a proper posterior distribution. So this work was led by my former student, Tree Nguyen, who is now a Sierra Fellow. And I promise we didn't pick the worst ones looking for Jane's analysis just to make them look bad. But for two galaxies, red and blue, with gamma equals 0 and gamma equals 1, this is what you would get with Jane's analysis. Again, this is Jane's analysis, not assuming any fancy feature. There has been work that includes higher order moments that does a little bit better. While with our graph neural network, we actually are much, much better suited or able to disentangle the inner profile for gamma equals 0 and gamma equals 1. This is using 100 stars, and it's with 0 error in the measurements. So again, in the best of cases. Of course, as I was saying, these are idealized, and what we want is to actually do this in slightly more realistic environments before we can safely apply it to data. And for that, we used the satellites of fire and tried to apply it. Again, what we are not training on any of these simulations. So what we're training on is 10 million realizations where we actually put in the potential and put in the density profile where everything is very well controlled. We did this for cold dark matter and self-interacting dark matter, mainly so we can see a variation in the inner profile and make sure that we get both of them. We're comparing here our GNN or graph MPE method to the Jane's analysis, although also in the paper we do compare it to GraphSphere, which is a different method that takes into account higher order moments for Jane's analysis. And they do somewhat similar. The interesting thing is that you can see that we're doing better at constraining, not in the places where you have a lot of stars, but rather when you have fewer stars. So this is for CDM, for example, for 86, we're a lot more constraining. For 35 stars, we do much better than Jane's analysis just because it doesn't have enough points. And the reason for it is because in Jane's analysis, what you're doing is you're taking all the points, you're projecting them into bins, where you're calculating the dispersion as a function of the radius in very few bins. So you're really losing a lot of the information, while here we're actually taking into account all of it. Great. Well, the thing is about dwarfs is that they can get tidally disrupted. So if you have dwarfs here, and this is the Milky Way, after some point there is a gravitational potential kind of gradient between the two sides, which is why some of our dwarfs, although if you can only see the inner part, you might not know that it has tidal tails and is currently being tidally disrupted, even if you only see the middle part. And indeed, my former postdoc, Nora Ship, who is now an assistant professor at University of Washington, has looked into this and put on LSST glasses to figure out exactly what you would expect from LSST. And found, and there are lots of plots here, and I don't think I have enough time, so I'll go quickly, but basically found that for a lot of the satellites, what you can have quite a few with undetectable tails. So undetectable tails, basically, you are only looking at the progenitor, you think it's a satellite or a galaxy, but it's actually being tidally disrupted and it's a stream. The reason that this is important is because for those situations, what you want to be building in density profile, you don't want it to be biased by these invisible or undetectable tails. So what we did here is look at how well we can reconstruct Vmax and the mass, as I will show in the next slide, for the less tidally disrupted and the more tidally disrupted systems for both CDM and SIDM, just so we can, again, get a variation on the inner profile, and we seem to be doing pretty well. It's good to also see it fail, and indeed it does. In reconstructing the mass for the smaller systems right here, where basically you end up over-predicting the mass. And this makes sense because you're extremely tidally disrupted for a very small galaxy from the beginning. So, and it kind of, basically the outer part is getting kind of disintegrated. So if you're extrapolating your density, you're definitely going to overshoot, especially for these small systems. So that kind of gives us a little bit more confidence of that it's doing exactly what it's supposed to be doing, even in its failure modes. So we've got a lot of work to do to apply to data. So right now we're looking to making sure that we're not getting any biases from selection functions, because selection functions are quite painful for dwarfs, and of course incorporating the errors and the uncertainties. So hopefully in the last hour-ish, you guys enjoyed my personal tour of the dark matter in the Milky Way. And yeah, I'm happy to take any questions. Thank you.
Questions?
Yeah.
Can you say more about the tools you're using, the sort of diffusion model, large scale structure type stuff?
Oh, for the diffusion model, yeah. So this is work by Carol. I don't know. Yeah, yeah. So we're working with her on this, and she's done it for, I think, 2D maps, and then she had a more recent paper for 3D maps of basically galaxy maps and trying to figure out what is the underlying dark matter structure, the large dark matter structure. She's doing this with, I think, Illustrious, one of the simulations, and it seems to be doing well. What we are thinking about, and I think she's doing it separately as well, is trying to, so what we've tried so far is just the 2D map where we just like kind of look at the inner, I don't know, I think he was looking at the inner 50 kiloparsec of the DREAMS collaboration simulations, just because we'll have quite a few to train on. And what we've been doing is taking the stellar distribution, taking out like the most kind of, it's kind of almost like the monopole, like the dominant kind of density profile, and then looking for the extra part, like the extra variation, and that's what we're making the diffusion model kind of predict. It does well, and then it starts rotating the map, and it's like a whole thing that we're playing with. The next thing that we're going to do, that Xiaowei is doing now, is going from the 2D to the 3D, but ideally, I think we'll have the most information once we include the velocity fields, because we have those information. To build gravitational fields, what you actually want is accelerations. We don't have accelerations, so we're going to give it velocities, and it's going to make some assumptions about how equilibrated things are to try to extract anything else. So that's kind of where we are. Yeah.
Following up on this point you're making about kind of the dispersion around whatever, I mean, at the beginning you were making the point that depending on your dark matter model, you either smooth out or you're very lumpy, and that impacts like the core.
Yeah.
But doesn't it also kind of impacts the lumpiness and the structure out in the halo or something? And so I wondered, and of course you're averaging over that in a James model,
Yes.
in a sense, because you're, you know, but this sort of treatment you're adopting now where you're like looking at the sort of full dispersion of a bunch of stars, do you have information there even at larger scales?
Oh,
in your modeling from kind of like how far you are from a smooth equilibrium model?
Definitely for the dwarfs. Oh, sorry, not for the dwarfs. For the Milky Way simulations and DREAMS, yes, we do have those, and you can kind of see that there is like there is kind of like a bit of a dipole that does show up when you take out the big moment, and then
Mm-hmm.
and you can kind of see the spots of like satellites.
Okay,
Yeah,
nice.
just kind of seeing those.
Yeah.
So having that, hopefully, well, we'll see how well it does eventually to get it accurately, and that will actually do tell us a little bit about the structure.
And so in
Yeah.
that case, you're dominated by the sort of out of equilibrium component
Yes,
rather
exactly.
than like small scale structure.
The small
in
scale
dark
structure.
matter. Okay.
That is true. Yeah,
Okay.
just especially for the inner part. I mean, the other
Makes
thing about
sense.
looking for small scale structure is that we are looking into analyzing we built this anomaly detection method to look for streams,
Yeah.
and that we're now kind of following up on because we had like 100 stream candidates. Again, anomaly detection found. It doesn't mean that they're all streams. They're classified by significance, but what we're looking for now is trying to make sure that we get the right membership for each one, and then trying to see if there are some density perturbations that can tell us about some dark subhalos, passages, and stuff, and trying to constrain this.
Cool.
So lots of fun.
Just like on the topic of streams, so as far as I understand, like most of what you get out of it is if you have a kick from a dark matter subhalo passing through, you're going to get some disruption, and you can model that disruption then and get some idea of where these halos are. Most of this work seems to be looking at the like actual internal structure of the halo itself. Is there any way to like discern that from a stream, or are you just getting like the mass of these objects?
So, I mean, to first order, getting the mass and the concentration of whatever dark subhalo, it can tell you a lot. In particular about the warm dark matter models that you get, right? Like, is there a cutoff in the power spectrum? If you're going all the way down and you find something small, great. That kind of tells you about that. The tells you also about a mass concentration relation that also is for the inner part. I think, at least, I think these are the things that we can get to first order. Second order, there will be kind of small perturbations and how much they're kind of dispersed around the galaxy and stuff, but I think that's going to be a little bit of a while to get there, so we have a much better understanding of those models.
Good, thank you.
Well, let's thank Lina one more time.
Thank you.